So hello everyone. On the last one we have discussed about the working principle of the transformer and its EMF equation. Alright, so let's move further in the same order. On the last one we have derived E1 is equals to 4.445 m f T1. This is the EMF equation for primary side, and E2 in the similar manner we have got 4.445 m f T2. Alright, so now let's see further from this equation, that is, let's consider 1 and 2 over here. So from equation number 1 we can conclude that E1 upon T1, this will be equals to 4.4455 m into f. Alright, equation number 3. And similarly from equation number 2 we will get E2 by T2, this will be equals to 4.445 m into f. Alright, so from equation number 3 and 4 we got, from equation 3 and 4, since the right hand side of both the above equations are same, we will get E1 upon T1. E1 upon T1 becomes equals to E2 by T2. Alright, and from here E1 by E2 will be equals to T1 by T2. This is simply the turns ratio, which is equals to the ratio of the EMF on the primary side and the secondary side. And T1 by T2, this is simply known as turns ratio. Alright, and this turns ratio is denoted by T1 by T2 is denoted by A. Okay, so in the transformer, in the practical transformer, we all know that there is a very little difference between V1 and E1 and V2 E2. So if we consider that V1 is equals to E1 and V2 is equals to E2, then this equation will become V1 by V2 will be equals to T1 by T2 is equals to A. This is what we got from here. Okay, so let's move further. Now let's discuss about the transformer on no load. Now a transformer is said to be at no load when the secondary winding is open circuited. Secondary winding open circuited. Okay, when there is no load connected on the secondary side, then obviously it is open circuited. Okay, the transformer is said to be at no load. One point is this, and okay, the secondary current is 0. Secondary current is 0. When there is no load, then no current will flow at the load side. So when the open circuit is there, then no current will flow on the secondary side, so the current should be 0. Okay, so when alternating voltage is applied to the primary, when the transformer is there, simply you can see that this is the transformer. Okay, we are giving the supply V1 over here. Okay, and we don't have any load. This was the load which is connected over here, but since we are considering this at no load, so this is open circuited. When this is open circuited, no current will flow through this circuit. Okay, now but the supply on the primary side is continuously coming. Okay, तो जब हम प्राइमरी साइड पे सप्लाई देंगे, when an alternating voltage is applied on the primary side, this is the alternating voltage which is applied to the primary side, a small current I0 flows in the primary. I0 flows in the primary. Okay. Now this I naught is called no load current of the transformer. I naught is called no load current of the transformer. All right. Now this I naught consists of two components. I naught consists of two components, which is I mu and IW. Now what is I mu and IW? This I mu is called magnetizing component. I mu is called magnetizing component, and this IW is called the active component. Active component, and this IW supplies the hysteresis and the eddy current losses in the core, and the negligible I square R losses, eddy current and hysteresis losses in the core, and negligible I square R loss, okay, in the primary winding. So this is responsible for these components, and I mu is responsible for the magnetizing. It is a magnetizing component which is used to magnetize the circuit. All right. IW is also called that the active component, and this I mu is called the reactive component. We will discuss further also about this. Okay, let's move further. Now I mu, let's consider first I mu. It is a magnetizing component, as I have already told you. It magnetizes the core, okay. One thing is this, or in other words you can say that it sets up the flux in the core, and therefore it sets up flux in the core, okay. Therefore I mu, since it is creating or setting the flux in the core, I mu is in phase with phi m. all right. जब ये फ्लक्स क्रिएट कर रहा है तो फ्लक्स एंड दिस कंपोनेंट आई म्यू, ये दोनों एक ही फेज में होंगे. द करंट आई म्यू इज ऑल्सो कॉल्ड रिएक्टिव कंपोनेंट, एज आई हैव ऑलरेडी टोल्ड यू. आई म्यू इज ऑल्सो कॉल्ड reactive component, and or you can say that, or it is also called as Watt-less component. Watt-less component of no load current. All right. So this is all about I mu. Now let's discuss a few things about IW. What is this? IW is simply, as I have told you earlier, it supplies hysteresis and eddy current losses in the core, and also negligible, just remember negligible I square R loss in the primary winding. Okay, so this is so simple. Now this component IW is called active component. IW is called active component, or watt full component, watt full, this is that was I mu is the watt less component, and this is watt full component of no load current, that is I naught. All right. Now it is in phase with the applied voltage. It is not in phase with the flux. It is in phase with V1, that is the supply voltage. And now this I naught, which is the sum of I mu plus IW. This is it is approximately 3 to 5% of the rated current of the primary side. All right. So this is all about the I mu and IW. Let's move further and see the phasor diagram at no load. So as we have already discussed few things about the watt full and watt less component. So let's draw this line, okay, and this line, okay. We are not mentioning anything yet. So let's consider this as phi m. Now since this is phi m, as we have already discussed about that the I mu, that is a magnetizing component, this is in phase with phi m. So as we have told you, I mu is in phase with phi m. All right. This is V1. So voltage and the flux, voltage and the current 90° apart over here. And the component IW, as we have already told you, IW is in phase with V1, okay. And in the transformer, you know that V1 and I1 should be opposite to each other, because according to Lenz's law. So E1 should be here, and E2 and E1 are generating, the source which is producing is the same, so both of them should be in phase, okay, E1 and E2. So what we need to do, we need to calculate, we need to draw I naught, and I naught is the sum of simply IW and I mu. You all know that parallelogram and all those methods you have studied earlier. So this will become like this. So I mu is this one, sorry, I naught is this one. All right. So from this phasor diagram we can see that this is the phasor diagram of the transformer at a no load condition, when there is no load at the secondary side and the open circuit on the secondary side. Okay. Now we know that phi is the flux for the transformer, should be phi equals phi m sine omega t. All right. From here we can see that E1, there is a flux EMF on the primary side, should be equals to E1m sine omega t minus pi by 2, and E2 should be equals to E2m sine omega t minus pi by 2. We have already calculated these EMF equations earlier. Okay, and from the phasor diagram you can see that from the phasor diagram we haven't mentioned this angle. This angle should be equals to phi naught. Okay, this is a no load power factor angle. Phi naught is what? No load power factor angle. All right. So from this phasor diagram you can see that IW equals to what? IW equals to I naught cos phi naught, okay. I mu equals to I naught sine phi naught, okay, and I naught should become equals to IW square plus I mu square root, okay. And from here cos phi naught, that is a power factor, cos phi naught should be equals to IW upon I naught, IW upon I naught, yes. So This is all about the phasor diagram. All right. So thank you. Thanks a lot